Throughout the 20th century, structural engineering relied on a straightforward rule. Achieving integrity required adding mass and using isotropic materials, substances that are uniformly rigid in every direction. This logic is effective for civil infrastructure, like concrete and steel bridges. But importing this rigidity into human biology creates a mechanical mismatch that eventually destabilizes host tissue. The primary issue with using rigid metals like titanium for joint or bone replacement is a localized biological complication known as stress shielding. This diagram illustrates exactly how stress shielding breaks down human tissue. On the left, healthy bone naturally absorbs downward mechanical forces. But on the right, when a solid titanium implant is introduced, its high stiffness causes it to absorb the entirety of that load. Because bone tissue requires physical stress to maintain its density, the unloaded bone surrounding the metal begins to thin and eventually resorbs. Beyond this biological response, metal implants create a diagnostic challenge. Their high density generates massive artifacts in MRI and CT scans, effectively obscuring the postoperative complications that surgeons need to monitor. Using isotropic metals forces a choice between structural strength and biological health. The implant remains intact, but the very bone it supports is lost. Resolving this conflict requires a different class of material, carbon fiber composites. The defining mechanical advantage of carbon fiber is anisotropy. Instead of being uniformly stiff, engineers can align individual carbon fibers to dictate exactly where a structure is rigid and where it yields. This selective architecture separates structural strength from overall mass. It allows engineers to tune the material's properties to match the specific mechanical profile of the bone or tissue it replaces. This tunable capability is currently being applied across 3 distinct scales: macroscopic load-bearing structures, mesoscopic kinetic actuators, and nanoscale cellular integration. By manipulating the hierarchical architecture of carbon, engineers can create biomimetic implants that adapt to human physiology, rather than forcing the body to adapt. Posterior spinal fixation devices present one of the most difficult load-bearing challenges in orthopedics. These rods must stabilize the spine and bear significant shear forces without fatiguing or fracturing. Early attempts to move away from metal used short fiber carbon reinforced plastics, or CFRP. However, these materials could not match the raw strength of traditional titanium alloys. The deficiency lies in the short fibers themselves. They lack the continuous end-to-end alignment necessary to transfer heavy mechanical loads smoothly across the entire length of the rod. The architectural solution is long fiber CFRP. By utilizing continuous, unbroken carbon strands aligned precisely along the rod's primary axis, engineers can distribute forces seamlessly. This chart compares maximum bending loads across implant materials. Short fiber CFRP and PEEK fail at low thresholds. Titanium and cobalt chrome withstand significantly more force, but long fiber CFRP reaches the highest threshold. When isolated against the current clinical standard, the long fiber carbon rod achieves 120% of the strength of a titanium alloy rod. These metrics are verified using the ASTM F2193 standard, which uses 4-point bending tests to ensure the material can endure heavy load cycles over time without succumbing to fatigue. Beyond mechanical strength, carbon offers a diagnostic advantage. On the left, a titanium rod produces a massive, obscuring starburst artifact on a simulated MRI scan. On the right, the carbon fiber rod is radiolucent, yielding a clean, transparent cross-section where the surrounding tissue is visible. This clarity is critical for procedures like stereotactic radiosurgery for spinal tumors, where oncologists must precisely target radiation at returning cancer cells without damaging the adjacent spinal cord. Continuous fiber alignment solves both the macromechanical load requirements and the imaging blind spots inherent in spinal fusion. At the meso level, the engineering problem shifts from static load-bearing to active movement, the development of soft robotics and biomimetic actuators. Designing artificial muscle requires balancing 2 opposing properties. The material must allow for large reversible deformations, yet remain stiff enough to generate high output force. To achieve this, researchers use a photothermal composite material. They encapsulate light-absorbing graphene inside a soft, highly flexible polymer matrix called PDMS. The mechanism behind this is photothermal conversion. When struck by a near-infrared laser, the graphene rapidly absorbs the light and converts it into thermal energy. This diagram illustrates the behavior of the unreinforced polymer. When the material heats up, the PDMS expands isotropically. The thermal energy pushes outward equally in all directions, causing the block to simply bloat in place. The kinetic energy is wasted. To control this energy, engineers embed a highly oriented carbon fiber skeleton directly into the polymer matrix. This structural addition mimics a natural biological musculoskeletal system, acting as a rigid, longitudinal constraint within the soft tissue. When heated, the rigid carbon skeleton resists longitudinal stretching. Horizontal expansion is blocked, forcing the thermal energy into a targeted directional bend. This yields an 89.75-degree curve and a 2.56 times increase in output force. Applying a rigid structural constraint is what allows engineers to convert thermal expansion into functional biomechanical work. At the nanoscale interface, structural engineering must successfully integrate with living cellular biology. Pure carbon matrices encounter a distinct limitation here. While they are biocompatible and non-toxic, they are biologically inert. For an implant to succeed long-term, it must achieve osteoinduction. The material must actively signal native bone cells to attach and rebuild. Engineers start with a base architectural scaffold made of electrospun carbon nanofibers. This creates a foundation that mimics the microscopic, porous scale of the natural extracellular matrix. To bridge the gap between this inert support and active tissue regeneration, the scaffold is reinforced with specialized bioceramics, specifically hydroxyapatite and bioactive glasses. During hydrothermal functionalization, intense heat and pressure cause calcium and phosphate ions to bond to the carbon, nucleating into rough, crystalline nodes. This altered topography causes fluid to spread rapidly, confirming the high wettability required for cellular anchoring. Once implanted, the bioceramic scaffold initiates a localized burst of calcium ions into the surrounding environment. This release of calcium acts as a signaling mechanism, cueing local Mg63 bone cells to begin generating new tissue matrix. The biological data confirms this cellular activity. HA-doped carbon triggers significant increases in alkaline phosphatase and osteocalcin expression, ultimately accelerating the mineralization process in the body. Through nanoscale hydrothermal doping, an inert structural fiber is transformed into a generative, living tissue bed. As the camera pushes inward, across all three scales, carbon's value in biomedicine stems from its structural tunability. It separates strength from mass and shape. We see this in continuous long fiber alignment for macro load transfer, and skeletal geometries for mesoscopic force direction, and hydrothermally doped nanofiber meshes for biochemical integration. This multifunctional composite approach contrasts with the traditional use of isotropic metals, which require the body to adapt to the material's rigidity. The future of tissue engineering and implant design requires abandoning materials that fight the physiological environment in favor of composites that seamlessly adapt to it.